Hello students, this is the video lecture for Physics 5054 GC O-Levels, and our topic for today is turning effects of forces. So my name is Faraz Khan, and the learning outcomes for today are moments, center of mass, and stability. Now when we're looking at moments, you've got to understand that uh, it's very important that we take into consideration the distance when we're applying forces at different things. Like, you know that a doorknob is towards the end of the door, not by the hinge, but on the other end. When you're opening a bottle cap, a can opener allows you to do it easily with less force in comparison to when you do it with your hands. What we can take into account with both of these examples is that distance from the pivot is very crucial and determines how much force is required to get the job done. Now, the moment of a force is the product of the force and the perpendicular distance from the pivot to the line of the action of the force. The moment of a force is equals to force into the perpendicular distance, and the SI unit for the moment of a force is Newton meter. It is a vector quantity, has got both magnitude and direction. When more than one force acts in one direction, their overall turning effect is the sum of their moments. Now, we've got to understand the anti-clockwise and clockwise motion first. So, let's say we've got this is my pivot, and then we've got this. Let's say this red dot here is the hinge, and that's a door, or if the red dot is a pivot, then the red line is the beam. Now, force is moving upwards with will move this in this direction. So the type of movement is anti-clockwise. If the direction is downwards and the movement is on this end, then this is clockwise. So anti-clockwise and clockwise moments. Now if all the moments of all the forces are acting in one direction, the turning effect is the sum of their moments. If they are in opposing direction, then obviously the difference will be taken, and we're going to look at that in the next slides and also in the coming practice examples. Now, principle of moments. For a system to be in equilibrium, the sum of the clockwise moment must be equal to the sum of anti-clockwise moments. Condition of the equilibrium is the resultant force acting is zero or the forces are balanced. The resultant moment about the pivot has to be zero. So what we're looking at here is let's say that we've got this little pivot point with a beam right here. Now the forces, the anti-clockwise and the clockwise forces, both these forces need to balance each other out. So the forces, let's say we've got a few different objects here. So we've got an object here, and we've got an object here. This one is putting a force right here, and the other one is acting towards this side. When both of these forces are equal, then we can come out and say that this beam is in equilibrium. These both forces have to be equal to each other. Now let's say if one is heavier than the other, let's say the blue object is heavier than the pink object, the blue object needs to move closer to the pivot point. If let's just say that the blue is heavier, it needs to move towards the pivot point to balance this beam. Because as we discussed, it's the force into the perpendicular distance from the pivot line. So if the force is greater, the distance needs to be shortened to balance the clockwise and the anti-clockwise motions about the pivot. The center of gravity of an object is defined as a point through which its whole weight appears to act for any orientation of the object. Now in this point, in this case, the pivot is by the center line of the beam. So the weight is acting right at the pivot. But if the pivot was not here, pivot was somewhere here, or then the weight will be an additional force with the distance from the pivot line. All right. And then we will also look at if it's the anti-clockwise or the clockwise moment. Now, moving on to the center of mass, we've got three different types of equilibrium. We've got stable equilibrium, we've got unstable equilibrium, and we've got neutral equilibrium. So, for the stable equilibrium, we need to understand a few points, which are that the center of gravity rises and then falls back again. Now, in stable equilibrium, the object, when tilted, slightly returns to its original position without toppling. And it's because that the center of gravity rises and then falls back again. Is that the line of the action of the weight lies inside the base area in the base area, and the anti-clockwise moment of the weight W about the point of contact causes it to come back to its original position. Now let me give you an example of a stable equilibrium. Now if you've got our base here, let's say, and then we are to draw an object with stable equilibrium. This is an object with stable equilibrium. Now it's got its weight acting downwards, right from the center. And when you tilt it slightly, it comes back to the original position. It's got a bigger base. But if you're looking at unstable equilibriums, let's just say this is our base now, and we make an unstable equilibrium. You know, when we topple this, that the center of gravity is much higher on this, object as compared to the stable one. It's very much closer to the base in stable equilibrium, but it's very high in the unstable equilibrium. And when the center of the gravity falls, when you topple the object, it continues to fall further, and the line of action of the weight lies outside the base area. So now this weight was acting inside the base area. This, however, when you topple it, will fall outside the base area. And the clockwise movement of the weight about the point of contact causes the toppling effect. Now let's move on to the neutral equilibrium, where even if you topple the object, the center of gravity would remain the same. So let's say you've got a box here. When you topple it, let's say you give two topples, two rotations, and the box is right there again. The center of gravity does not change. It's not moving up and down as compared to the other cones. The line of the action of the weight acting and the upward contact force always coincide, and there is no moment provided by the weight, and hence these objects are in neutral equilibrium. This is unstable equilibrium and this is stable equilibrium. Now moving on to the center of gravity. The center of gravity of an object is defined as the point through which weight appears to act. It depends on the distribution of mass. The center of gravity may also lie outside the object. For example, a ring. Now, how to calculate the center of gravity for irregular objects? So what we do with the irregular object is we make different holes at the end of the irregular object and make sure that they've got considerable distance between them. So then we suspend that irregular object through one of the holes using a pin. We hang it on a plumb line and we draw that plumb line on that object. So let's say you've got an object here. That's kind of like this. And what you do is you make small holes at the end of the objects. Make sure you've got enough distance between them. And then you hang them on the plumb line by these. So when you drop them, when you hang them, you'll see, and when you draw the plumb lines on these things will those those lines that you've drawn would somewhat, look like this, and where these lines match, the intersection point is basically your center of gravity of that irregular shape. So what you need to make sure is that the hole should be small so that not too much of the lamina is removed. Obviously, when you pick out a hole, it messes with the weight a little bit, so make sure that the hole is as small as possible. The lamina should be free to swing about its point of suspension, and then the intersection, after you've drawn all of the plumb lines, would give you the center of gravity. Moving on to stability. Stability refers to the ability of the object to regain its original position after it has been tilted slightly. Obviously, we've discussed this with stable equilibrium, unstable equilibrium, and usual equilibrium. When no such moment is created, uh, when you're looking to determine the stability of an object, make sure that the area of its space should be as wide as possible, and the center of gravity should be as low as possible. Now, moving on to practice examples. Question number 1: a uniform horizontal beam pivoted at its right end is in equilibrium. A force of 60 Newton acts vertically upwards on the beam as shown. So we're going to look at the opposing forces. Clockwise equals to anti-clockwise. So clockwise is 60 into 50 equals to the weight into 30. All right. So when you're going to do the calculation for it, your answer should be 100 newtons. So 100 into 30 equals to 60 into 50. That's the clockwise equals to the anti-clockwise forces, both moments. And that's when the beam is in equilibrium. All right, moving on to the next. 4 table lamps are shown along with the position M with the center mass in each case. Which lamp is the most stable? Now, the one with the greatest base area and the lowest center of gravity is the one that's more stable. So A is the correct answer for this. Moving on to the next, the total weight of the load on the wheelbarrow shown is 600 newtons. What is the size of force F needed to lift the loaded wheelbarrow? All right, so you've got 600 newtons acting downwards at the distance of 70, and that would be equal to a force acting at the distance of 120. So your answer would be 350 newtons. All right. So moving on to the next, the 6th question is also the same. You're going to look at the clockwise equals to the anti-clockwise forces. 2 into 10 plus 4 into 20 equals to u into 40. And then you can go on to find the answer of this question as well. All right, a car is designed to be stable to achieve good stability. Where is the center of the mass of the car? As low in the car as possible. The lower the center of gravity, the stable the car is. A man uses a clay to make a pot. He wants the pot to be as stable as possible when placed in flat surface. Which 2 features of the pot must the man consider? The area of the base and the height of the center of gravity. And that is the correct answer. The area should be as wide as possible, and the height should be as low. What affects the stability of an object? The base area and the location of the center of mass. Alright, so two stretch springs X and Y are attached to one end of a meter rule as shown. A weight W is hung from the other end. A pivot is the center of the rule. Now the weight W is moved towards the pivot. How does the extension of each spring change? So when you're moving it towards the pivot, the force, the anti-clockwise force would decrease. So the X would increase and the Y should also decrease with it for it to be inequally. A beam pivoted at one end has a force of 5 Newton acting vertically upwards on it as shown. The beam is in equilibrium. We're going to do the same thing here again. Clockwise equals to anti-clockwise. 5 into 2 equals to weight into 5. And then you can go on to find the weight. The masses X and Y are placed on opposite sides of the center of a uniform meter rule, which is pivoted at its center. Which combination of masses and the distance balances the rule? You're going to look at that xp equals to ys, and then you can go on to find the answer for this, which I believe should be, yes, it's C. So C would be the correct answer for this, because 400 into 12 equals to 16 into 300. All right, would be stable. The student balances a non-uniform object on a pivot. To do this, a weight is suspended near the left hand end of the object. Where is the center of the mass? Now, since the weight is already attached, you can say that the center of mass would be towards the D. Moving on to the next, to determine the location of the center of the mass, the student then repeats the experiment but with one change. What is the change? Alright, so the question is not complete. Here we move on to the next one. A metal cone with a circular base is placed on a flat surface. The stability of the cone depends on the diameter of the base and the position of its center of the mass. Now the stability of the bus is tested by tilting it on a ramp. Where is the center of the mass? What you're going to do is you're going to drop lines from these and see where it crosses. It should be at C. A driver's foot presses with a steady force 200 Newton on a pedal in a car as shown. What is the force F pulling on the piston? The same thing. Clockwise equal to anti-clockwise. So 200 into 40 equals to 5 into F. And then you can go on to find the F. Thanks a lot. This would be the end of this chapter. If you've got any questions, put them down in the comment box and I will reply to them. Happy learning.